a voxel. Okay, so basically they are trying to trace the blood or the neurons direction from your brain. I mean, sometimes you can see these pictures. You have it's very colorful ones, okay? And very often each voxel has one direction, but it becomes difficult if they are almost tangent to each other or they cross each other, okay? So that's what they are trying to determine by using they do this type of decomposition to determine whether there's one crossing or they're almost. So they have, if usually it's one direction, they try to see whether it's crossing like this or something like this. Okay?
The voxel is a 3D pixel, right?
And this is, yeah, so this is a voxel usually. Okay? So what they usually do is they just try to measure this, or sometimes it's a circle, spherical, and they try to measure different direction. So of course the dream is if you can do this, then you can use fewer samples. Because for example, it's a 3D, sometimes they need 64 measurements around each direction. Okay, so basically, okay, I can point the paper. The same problem can be formulated like this. Okay, and the idea is that you don't need that many measurements. Okay, but I'm not aware of people really using this for that. I've read papers about it. They try to, and then also as you can see, this method is the connection is to a polynomial. So of course now if we have some tool from Padé from other places, okay, the ambition is to see whether we can borrow some tools from there.
Yeah, because I'm recently looking at tensor decompositions myself, but it's not clear to me when people are talking about low rank tensor decomposition, yes, how low the rank usually are.
Okay, but first of all, this is a symmetric tensor. So when people talk tensor decomposition, first of all, it may not be a symmetric one.
Right.
Okay, and of course this one we link to the univariate Padé, but for the multivariate Padé, of course, we think can be more general. But this one, because we want to keep the same thing along the talk, in the talk. So this is symmetric tensor. So I know that sometimes people comes with a different definition of the rank. They have different ways to decompose. So this is one of the special case. But interestingly, this can be connected to some of the algebraic problems. For example, they also use Sylvester matrix. So actually, the Prony's this is called wearing decomposition. Wearing. Okay. So and connect to the Sylvester matrix. So recently, lots of people from computer algebra are using the tools from algebra to deal with this problem. Okay. So it probably corresponds to some of the tensor decomposition that you learned from the literature, but this is a very specific case.
Yeah. For my impression is that when the R is really small, some techniques can be useful, and when the R is not that small, we have to switch to other techniques.
Correct, but in this case, at this example, I only have R is equals 2.
Right.
But you have seen the exponential analysis, they deal with 3 or 4 or 5, very often to 10, they don't have problem. So the question is, are these tools helpful here, or the other way around?
Yeah.
One more question about computational possibilities. You showed, for instance, reduction to Henkel solving, polynomial root finding, and then Vandermonde type,
yes,
transpose Vandermonde. Then there was Padé approach leading to generalized eigenproblem.
Yes.
It seems that second option is much better numerically, because Henkel solving is already can already be well conditioned. Polynomial root finding with inexact coefficients very well ill conditioned. Then Vandermonde also can be ill conditioned. Now I think then maybe the user choice would be eigen-solving, generalized eigen-solving. It seems to be
Yes.
numerically much better.
Yes, and also there's because in my first slide we said that in the application they have the problem so-called directions of arrival. Over there they have another method. It's called S-street. Okay. So the Hankel matrix is a special case of this. So they also use they compute the eigenvectors.
Okay.
So they do SVD, and so SVD is involved. So yeah, so depends
Okay,
on depends what people want to do.
So first part was historical, but for real life actually you
Yes,
need,
yes. In the real life,
generalized
usually we use a generalized eigenvalue. We don't go back to the root
yeah,
finding.
yeah. Well, technically it's interesting how it came.
Yes.
So Pronis approach
Yes.
is important, but essentially we
Yeah,
have no
essentially, people
generalized
use
eigenvalue.
a singular value or or
Generalized
a
eigenvalue.
generalized eigenvalue. And then also using the polynomial, we can connect to the orthogonal polynomial. So
Yeah, that would be interesting to learn a little bit more, but
yes,
for today it's
yes, for today it's okay.
yeah,
Yes,
yeah.
yes. Well, thank you very much.